Hey, it's Mr. Shrum. How's it going? Last time we looked at acids and bases and pH, and now we're going to look at atoms in chemical reactions. And hopefully by the end of this lesson, we're going to develop a model that shows that atoms are conserved in chemical reactions. So for a warm-up, we got a deli question. Ryan works at a deli. One day, his younger sister, Meg, visited him at the deli and happened to look at his notebook. She couldn't understand Ryan's entries. She saw W2C, W2V, RHC, yada, yada. Ryan explained that he used a code for the sandwiches and other items he sold. For example, W meant wheat bread, and the subscript 2 meant 2 slices. C meant chicken, and Meg spent a little time figuring out the meaning of each symbol, and it was a lot of fun. So she says. So here are the codes for the ingredients: chicken, ham, cheese, vegetables, rye, and wheat bread. Rye is a type of bread. Select the correct answer. Which formula shows a sandwich with 2 slices of rye, R, bread, and 1 slice of turkey, T? Yeah, it's that one. Oh, I already did. There you go. During the lunch rush, Ryan made 10 sandwiches with 2 slices of rye bread and 1 slice of turkey. Which formula represents the sandwiches he made? So you can put 10 times 2 slices of rye, and 1 slice of turkey. So far, pretty easy, right? And this ties into how substances are represented at the atomic level. Substances are observed and their properties are measured in chemistry. All substances consist of elements, and elements consist of atoms. There are 92 elements found in nature. These elements combine in various ways to form other substances. More than 1 million substances are found on Earth. To make it easier to understand these combinations, scientists have given each element a symbol. Complete the following activity to learn how scientists use symbols and pictures to show the atoms in a substance. So here's a lesson activity: representations of carbon dioxide, or CO2. Here is what CO2 looks like in this illustration. Answer the following questions. Use the periodic table to find the names of elements. So part A. One way to represent a substance is with a chemical formula. In the formula CO2, what do the symbols C and O refer to? Well, carbon for C, O is for oxygen. So in CO2, why does the O have a little 2 after it? Well, that subscript means there are 2 atoms of oxygen. So you have 1 atom of carbon and 2 atoms of oxygen. And another way to represent a substance is with a picture. What information does the picture provide about CO2? The picture gives information about how many atoms or how many kinds of atoms are in CO2 and how they are connected. So if you go back here, you see how we have the 2 oxygen molecules attached to the carbon atom. Another way to represent a substance is with its name. In this case, the substance's name is carbon dioxide. The prefix di means 2. The word oxide refers to oxygen. What information does the word dioxide provide? Well, it means there are 2 atoms of oxygen. So you see how the name ties in with the picture, and that ties in with the formula. It all makes sense once you understand. So let's review how chemical formulas show substances at the atomic level. A chemical formula tells us which atoms are present in the substance, and it gives us the ratio. Each atom comes from a specific element and is shown with a symbol. The periodic table lists the elements and their symbols. In many substances, a molecule is the smallest particle in the substance. Many chemical formulas show a molecule. And for example, the chemical formula for water is H2O. So you have H for hydrogen, O for oxygen, and the little 2 after the H means that there are 2 atoms of hydrogen. The absence of a subscript after the O means that there's only 1 atom of oxygen. The chemical formula tells us that a molecule of water has 2 hydrogen atoms and 1 oxygen atom. Easy peasy. So, nitrous oxide is the chemical name for laughing gas. What are the names and the number of atoms in a molecule of nitrous oxide? So we have N2O. There are 2 nitrogen atoms and 1 oxygen atoms. Here's another question. Carbon tetra chloride is a toxic liquid. A carbon tetrachloride molecule has 1 atom of carbon and 4 atoms of chlorine. Tetra is a prefix for 4. So you have 1 for carbon and 4 for chlorine. Potassium chloride is a white solid used in medicine. There's 1 atom of potassium for each atom of chlorine. So it's a 1-to-1 ratio. So we have KCl. Oh, and potassium is represented with a K because it is in another language that was derived from. Images of substances. So this ties back to how the images also give a similar type of information that the formulas do. So you have H2O. You can see there are 2 H's to every 1 O. And here's a few ways you can show that bond. So you have the written out, and then more of the visual, and then that's a different type of visualizing the bonds. So yeah, this is a molecule of water, H2O. And you can also learn about the chemical bonds that connect a substance's atoms. And we can look at that in the next page. So here we have liquid water on the left and sodium chloride. You can see how one looks more structured, crystalline, and the water is a bit more jumbled and messy. Water is made up of separate molecules, and table salt is connected more like a framework, it says. So more cleanly. Many liquid and gaseous substances, including water, are molecular. Most solid substances are networks. So most gases or liquids will look more like the left, whereas solids will look more like the right. Let's look at some more examples of substances. All right, so we have different pictures of molecular representation. We have oxygen, O2, a colorless gas in the atmosphere. Organisms need oxygen to conduct energy-releasing reactions. Oxygen is a molecular substance. Copper is a soft metal. Copper is an excellent conductor of heat and electricity. It's a network substance, so it looks more structured. Glucose, this is a formula for that, is a type of sugar that living organisms use in reactions that release energy. It's a molecular substance, meaning it looks less structured. Iron oxide, Fe2O3, is the chemical name for rust. Rust forms when iron is exposed to oxygen. So naturally we have iron and oxygen. Iron oxide is a network substance, so it looks more structured. Then you have methane. That is the main component of natural gas. Natural gas is a fossil fuel that provides energy. Methane is a molecular substance, so not as structured as some of the other ones. And in this activity, you're going to look at various atomic level representations of substances and then draw them. So I'll show you the pictures. So this is carbon monoxide, which is a molecular gas at room temperature. It's produced when a fuel burns with too little oxygen. And its chemical formula is this, CO. So for every carbon atom, you have one oxygen. Examine the drawing of a molecule. Each ring represents an atom of nitrogen. What's the chemical formula? Well, we have N2. Because there's two of them. Hopefully that makes sense. Examine the drawing of atoms of fool's gold. Fool's gold is, I'll show you, pyrite. So it's a mineral. It's an iron sulfide with the chemical formula FeS2. And it's one of the most abundant sulfide minerals. It's derived from the Greek stone or mineral which strikes fire. So pyro, think of pyrite. Despite being nicknamed fool's gold, it's sometimes found in association with small quantities of gold. So it's not always fool's gold if it shows up by gold. But yeah, anyway, interesting, fun fact. And this is what it looks like, the molecular substance. Do you think it's more molecular or more of a network? It's a network. It just looks a little less structured than some of these other ones. But you can see how all of the molecules are connected. Here's carbon dioxide. Here's carbon monoxide. Mono means one. Di means two. Different substances might have the same atoms, but they are combined in different ratios. The chemical formula for carbon dioxide is CO2. And the chemical formula for carbon monoxide is CO. There is a difference of one atom of oxygen in their molecular structure. So the two gases have different properties. Carbon dioxide is used by plants and is essential for life. Carbon monoxide is a deadly gas, on the other hand. So one's for life, one can kill you. So be careful. All right, and I think I'll stop that here for now, and we'll pick up here next time. But until then, have a good one. And if you have any questions, be sure to ask me in Canvas. All right, see you guys.